Title is synchronization in flux with large population. Here is outlines, mainly 3 parts after introduction, and present the main results, and then give some concluding remarks. And I will focus on the second and third part. So, as you may know, flocking is a class of a kind of a multi-agent system. So I'd like to begin my talk with some basic concepts of multi-agent systems. By agent, we mean you can mean many things. For example, the individual, particle, insects, birds, fish, people, robot, not depending on the context you're interested in. So as mentioned by our acting president, such a system, multi-agent systems, ranges from physical systems, biological systems, to social and economic systems and engineering systems. So you can see, here is a flocking of the birds. So besides the flock of the sheep, and also bee colony and ant colony, and here is a quite interesting paper published in Science in the year 2006. And I will take a little more time to explain this. So the results is very interesting. That shows at lower densities there was a lower incidence of alignment among individuals. Lower density, intermediate densities, the characterized by long periods of the collective rotational motion, with rapid spontaneous changes in direction. So for large densities, more interesting, the logs quickly adopted a common and persistent rotational direction. So I will back to similar phenomena later on using some mathematical model. So you can see cars and bicycles also can be regarded as multi-agent systems. Also flocks, also and the formation control in airplane and robotics. So by collective behaviors, here are some examples. The collective behavior can be a phase transition, or coordination, or synchronization, a consensus, clustering, aggregation, and so on. And so we have talked about agents. What is multi-agent systems? What is collective behaviors? I think a fundamental problem which has some kind of universality is how locally interacting agents lead to collective behaviors. It's a fundamental question, but very broad. And so I will try to understand and answer this problem for some specific class of systems. So first I will show you there are 3 categories of research on collective behaviors. The first one, I would say analysis. Given the interaction rules of the agents, what is the collective behavior of the overall system? This problem can be regarded as a bottom-up problem. The second problem related to multi-agent system design. Given the desired collective behavior, what are the interaction rules for agents? This kind of problem can be regarded as a top-down problem. The third kind is a control or soft control. Given the interaction rules of the agent, how to intervene in the collective behavior. So in this talk I will focus on the first problem and the third problem only. But I would like to mention that the second problem is directly related to distributed control design of multi-agent systems. I believe many colleagues in CTU are working in this direction. but I'm not going to talk about this. And so these are related to automation and automatic control in the area. Okay. Let's have a look at the basic model. So before establishing a mathematical model, let's have a look at some key features of multi-agent systems. Certainly, this is only partial features. So from the examples I showed just a moment ago, you can see such kind of system has some distributed and autonomous features and have a lot of local interactions, or maybe you also have global interactions. And the neighbors, I will define the neighbors later on. And neighbors may be dynamic, may change from time to time. And so the agents may have no physical connections. Okay, in order to carry on our mathematical analysis or quantitative analysis, we have to make further assumptions. So we assume that each agent makes decision according to local information. Certainly, you can have global information, but I think that when you have global information, our analysis is easier, in my opinion. Local information is much harder to analyze. So each agent also has a tendency to behave as other agents do in its neighborhood. Mathematically, let us have a look at the neighbors. There are two kinds of neighbors we are going to investigate, or two definitions for neighbor. The first definition for neighbor, we call that the geometric distance, using the geometric distance to define the neighbor. So let x t be the position, for example, the position of a ith agent. Okay, the distance between ith agent and the jth agent is measured by this. R can be regarded as a radius. Okay, radius was neighbor. So this is the neighbors of ith agent is defined like this, the geometric distance. So you can see it like this. So they're related but fundamentally different definition for distance. The topological distance defined like this. The neighbor of ith agent is defined as the nearest, m is a fixed number, m agent from ith current position. So this definition are different. So this usually results in undirected graph, and for this we will result in a direct graph. Okay.